Okay, really quick, we're going to go to the machine room, okay? We're going to name everything, we're going to go through everything really quick, and then we're going to come back here to this piece of paper, and we're going to learn about the entire system and the theory of how it works. Now, this video is 35 minutes. If you stick it out, I promise you, you understand the system like you never thought possible.
Okay, really quick, we're just going to do a quick run through of the rack. So first off, you have your compressor, then from there, you have your discharge line. Now, if you look down there, you're going to see something that's called a discharge header. Okay, this is where all your discharges go, right there, discharge header right here, super hot, okay? We're going to follow that all the way over here, right? This is high pressure, still comes right here. This is called your oil separator, okay? Now we're going to take a quick detour, it right comes off the bottom, that's your oil line, goes through, up, comes out here. This is your oil reservoir, you got your check valve, that goes all the way down, and that's going to land on your suction right there, and from there, it's going to come through here, down, out of your oil reservoir, through your oil filter, okay, through into your oil lines, and you're going to see it's going to come back behind there, into each one of those oil floats, oil regulators, whatever your company decides to call it. Now, after this oil separator, we're going to come here. This is a check valve. This is a hot defrost differential valve, all right? So you see, you look out of the back of that pipe, right there, see that line comes up, and now there's all the hot defrosts right there. And you can see that all those hot defrosts will go right into that suction side right there. Alrighty, and now that just dead end right there. Now we're going to keep moving down the cycle, high to low pressure, okay? Now we're up at this three-way valve. What does this three-way valve do? 2 water heaters. What's the other side? Return from water heater. What is going on with that guy? So what happens is, the hot gas comes here. When this is engaged, okay, so when that controller over there says, we want hot gas, hot water reclaim. This hot water comes out of there, goes in there, goes over there, goes through those tanks. Gives off its heat energy to those tanks, comes out of those tanks, come all the way back from water heater, come down here. Now then, see, comes through this loop over to here. 2 condenser, 2 condenser. Now this is your split three-way valve. Now, if let's say it's really low temperature out, they can make it so you're no longer using your water reclaim, and then it just goes right to your condenser for cold weather conditions. Alrighty. So now we have to the condenser, both of these lines. This is your 3-way split valve, right? So which one is on? Is anything on? Well, you can just feel it with your hand. This one's hot, so this one's on. So it's in split right now. Now if we look at this, we can see that this line comes out right here. What is this guy? Well, I don't know. Well, let's go find out. So we're going to follow that piping. And that piping is going to go outside. So let's take a look. Alrighty, so we're right here, okay? We're going to look over here, right? So we're going to feel them. Just kind of touch them. These ones are hot, so let's find where they go. All the way up there. There's your condenser. You see? So this one's hot, this one's cold. So this side of the condenser, this is one of the split sides. It's not working. Shut down. Not using it because it's so cold out. Got this one right here. Going over there. Going through the condenser. Then it comes out of there as a liquid. Now, you might be saying, but, you know, HVAC-R, Genuine HVAC-R guy, where is that other line? The other line's right here. Now let's follow it. Let's see where it goes. Following it. That goes into right there. What's that big thing? That big thing is a receiver. So what that smaller line does, and we'll go through it at the end of the video too on paper, what that smaller line does is that smaller line has a kind of like an EPR, but it's not an EPR, that regulates the pressure inside that receiver. Okay, so it allows discharged gas to go to that receiver to raise the pressure as needed in order to get the refrigerant out to the rack. That's what that small line's doing right there. So now we're going to look right here and we're going to say, oh, okay, here is our condensed liquid. We're going to follow that down. There's a check valve right here and right over there, so it doesn't go back up. It's going to come down here and to the receiver. Now that valve right there is called a holdback valve. Some call it, I think, holdback valve. And so what that does is that holds back the pressure in the condenser, okay, in order to make sure that the system still operates properly. And we'll go through that later in the video about how to set that and how other people do that. But now from here, right, we're going to go all the way down to the other side. So on this side of the receiver, you can see that line's coming out right here. that's our liquid out. So this is the liquid coming out of the receiver. So we're gonna follow that back to the building. Oh, what do you know? It goes back in the building. So it's gonna come in through the building, come down somewhere. You can see that comes in from over there, comes up through here, down through here, right through this filter dryer, up through here. Okay, now it's gonna come out here. Now this is gonna be kind of funky. Now you got one line coming out this way, one line going to the subcooler. Okay, so this one line comes down all the way across here, makes its own liquid header. All right, now it comes down, it pumps into this liquid header, and then those lines go out to the cases. Okay, but this one over here, this one is going to go through the subcooler, you see? Goes into this subcooler, gets blah, 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 gets subcooled, and I have playlists on how that works. Maybe I'll go through it a little bit at the end of the video. Comes up through here, comes out of there, and what do you know? What does this guy do? Following, goes into here. It makes another liquid header. Well, that's kind of strange that one's subcooled and one's not. Well, basically, one needs to be subcooled to have rated capacity, and the other one doesn't need to be subcooled. And it all boils down to efficiency, and we'll probably go over that when I get the pen and paper out. Now, from here, from this liquid header, it's going to go out to the cases. Just real quick, see the liquid line all the way out there. Go to the cases, go to the other corner, which I'm not going to very far to show you, but it's here. And we'll stick the line, put them out with the aluminum at the top. That's the HVAC coil, that's the suction side. And this is the line that the suction line. From the case, it'll come back here to the rack on that suction line to one of these things. This is an EPR valve, or sometimes it might be a suction stop valve, whatever, depending. From there it comes down into here, which is your suction header. Now if you look at, you can see different suction headers. Now this door is kind of hard to see it on, but for instance right here, you can see there's a divide there. There's actually nothing there. Kind of hard to see, but so this is like a separate group of piping. This is a separate group of piping, and this is a separate group of piping. And we can see that this is what is called a suction header bypass valve, or bypass line right there. So this is a suction header. Okay. The three different things are called suction groups. So 1, 2, 3, 3 distinct pressures that the compressors are aiming for. So there's 3 compressors on that suction group, 2 compressors on that suction group, 2 compressors on that suction group. Now from here, we come out of here, we go to here, which is the suction filter housing. This is a filter. It's kind of like a filter dryer. I'll explain more about it. Goes back in here, into the back of your compressor. So, yep, that's a rack in a nutshell. Now let's go to the pen and paper and learn a thing or two about it.
Okay, first off, we're going to start off with, refrigerant is not cold, okay? If we were to leave this system, like let's say you had a fully charged system, you left it for a month, okay? Didn't touch it, turned it off, okay? Everything would equalize. So the pressure would be like 70 psi, let's just use as an example, maybe 100 everywhere, okay? All your cases would be at the same temperature that's in your store. Okay, so everywhere, let's say it's 70 degrees outside, 70 degrees in your store, every single pipe would be 70 degrees, and every single case would be 70 degrees if that was the case, okay? So we're going to start off with that condition. What happens? So first, let's examine the compressor. What does the compressor do? Well, if you look inside the compressor, okay, you have this little, we're going to use a semi-hermetic as an example, and the same principles will work for a scroll, okay? So if you look inside your compressor, you have this piston that pushes up. Right, so what happens is, let's say at our condition where it's 70 on both sides, everything's equalized, okay? So what happens is, this pushes up, any refrigerant that's in there will be pushed out past this check valve right there. So this check valve, you can almost imagine it as it only opens up one way, right? So as that plunger goes back down, the piston goes back down, right? The check valve's going to close, and none of this refrigerant is going to get back through, okay? So what ends up happening is you're going to squish all the refrigerant out towards the 200 psi side. Then, as this piston goes down, you're only going to be left with very little refrigerant in there, if any at all. You might get out almost 99% of it. And if there's nothing in there, that is what we would call a vacuum. A area of pipe that has no molecules of refrigerant is a vacuum, okay? Well, technically what a vacuum is we have a normal pressure I believe it's around 17 psi, right, wherever we are in the world. That's just our normal atmospheric pressure. And anything under that is called a vacuum. Okay, so there's basically less molecules of refrigerant in this compressor than there even is outside just in the normal atmosphere. Okay, so what happens is when this piston goes up, pushes out all the molecules of refrigerant, it's going to go back down. And when it goes back down, it creates a low pressure in this compression chamber, okay, which is 1 psi. Now, if we go to the suction side, okay, in our system that has been left for a month, let's say it's going to be like 70 degrees, 70 psi, right? High pressure goes to low pressure. So that those molecules of refrigerant will naturally migrate into the compression chamber of the compressor, okay? Now, again, even if we look at a condition where it's operating normally at, let's say, 20 psi, okay? Again, you're going to have high to low. So that 20 psi is going to naturally be attracted to that 1 psi, and it's going to go over. So that is what starts our entire system from this dead system. It'll start pushing all the refrigerant out the discharge line. So now it's pushing it out of the discharge line, you see, right? So we're going to learn something quick. Please don't let your eyes gloss over, but we're going to learn the ideal gas law, okay? Now, super quick, okay? Basically, it's pressure. Okay, and I solved it for pressure. So pressure equals molar mass. So what is that? That's just how much stuff times R. That's just some constant. So every single gas is going to have a different one. Like 507 is going to be different than 404A. It's going to be different than 410A. It's just something that they have. Times temperature. Okay, we all know what temperature is over volume. Okay, volume is obviously like, like for instance here, right, this volume is changing, right? So from there it's squished in your compressor super tight, and then this piston goes down, which changes the volume, which will lower the pressure, because, right, the temperature doesn't change, but if you almost view it as there's the same amount of stuff stored in a larger space. Okay, so you can just kind of view this as if you can jam pack more stuff into a certain area, you're going to have more pressure. And if you raise the temperature, you're going to have more pressure. Okay, kind of basic, right? So that's how our entire system works. It is basically jamming more stuff in an area. So for this discharge line, okay, we have it coming out of the discharge line, right? It's going, and then we have our oil separator. So what happens is there's like a little screen inside this oil separator, almost like a screen window. Okay, and your discharge line is your discharge gas is hitting that screen, and when it hits that screen, the oil sticks to the screen and flows to the bottom of this oil separator and out the bottom into your oil reservoir. Okay, so now on the top of your oil reservoir, you're always going to have this line that goes to your suction group. Okay, so typically it'll go to your higher pressure suction group, and then right there, that's a check valve. So what that check valve is doing is that check valve has a 20 psi differential. So whatever this line is will be 20 psi higher than this suction side. Why? Well, remember, high goes to low, right? So this line is now 75 psi, right? This is your oil filter, and it's going to flow to our compressor. And in order to flow to our compressor, you have to have a high pressure to a low pressure. So it's flowing to the crankcase of the compressor, which is around your suction pressure. So you need this line to be higher than suction pressure. So when that discharge gas mixed with oil gets pushed into the oil reservoir, any PSI over 20 PSI over this suction pressure will get pushed out and push through there, and then this check valve will hold back 20 psi so it flows to your compressors. Okay, that's how your oil system works. Now from there you have this hot gas differential valve. What does that do? So what that does is when your system's going to go into hot gas, okay, it turns on this hot gas valve. Now you can just imagine this valve as a hole, like a little tiny hole, an orifice, okay? And what it's doing is when the solenoid engages, it's restricting the flow of refrigerant. Kind of like if you are at a bar or you're at a concert and you're all trying to get out the door, right? You're all trying to walk out. Everyone bunches together and there's a lot of pressure at the door. But on the other side of the door, there's less pressure, okay? Because there's more space to move. It's not a constriction, right? So what happens is, in order to raise this pressure, remember, okay, in order to raise pressure, you add more stuff or you raise the temperature. Okay, in this case, what we're doing is we're adding more stuff because now this cannot escape this line quick enough. Okay, so this raises the pressure on this side of the hot gas line, the hot gas defrost valve. Okay, so that's what will raise the pressure of everything in order for your hot gas to work properly. And we'll go through on the end how the hot gas works. Now, after your hot gas differential valve, you got your hot water reclaim three-way valve. So what happens is when your controller says, okay, we're operating at good enough conditions where we should reclaim the heat, that means they're using their excess heat in your refrigeration system to heat up your water. Okay, so what you do is you go to this valve, and now this valve redirects your refrigerant through your hot water tanks. And those tanks are basically condensers. So they're going to lower the temperature and condense your refrigerant down to a liquid. Now, it's not going to work fully. It might only do like 10% of it. So this is going to be a gas-liquid mixture. Okay, and now that's going to go to your split valve. Okay, and then at your split valve, okay, this will reduce the capacity of your condenser. So you have two sides of your condenser. And this split valve will turn off one side and leave one side on. Why would you want to do that? Because remember, this whole system runs off of pressure, high to low. So these compressors are artificially creating a high pressure side, right? And then you have a low pressure side, which is your suction. So in order to keep that pressure, to have the right pressure difference, which is about 100 psi over your suction. So if I have 55 psi, your minimum is 155 psi at your condenser. That's kind of your minimum that you need in order for this whole system to work. So by turning on and off different sides of the condenser, we can artificially create the pressure that we need. That's why you have different fans on for staging. Okay, is because your whole system, your controller, the brain of your system is trying to keep it at this sweet spot of condenser pressure. Okay, and remember, we can create pressure by adding more stuff or raising the temperature. Okay, so in this case, what we're doing is we're lowering the temperature by putting on more fans, or we're lowering the temperature by using more of the condenser to cool. Now, if you think of it as like if you pour a bunch of water in a bucket, okay, that water might sit in the bucket for a month before it evaporates. But if you spread that water all over a gym floor, it'll be evaporated in like an hour, okay? The same thing with the condenser. The more surface area it has to make contact with that air going over the coil, the more heat reduction capacity it has. So that's what this split valve does. Now from here we have this A8 and these two A8 valves, or it's also known as the holdback valves. The holdback valve, exactly as it sounds, holds back refrigerant for your condenser. Now typically, at least in the systems that I work on, these are not in play ever. Why? Because typically they are targeting 100 psi over your suction pressure. So this 55. So these would actually be set for 155, and these are for extreme weather conditions like -10, or it's for if your system is manually just you lose communication, it is set up so it will run anyway, and these valves are designed to run your system when your controller is not working, at least in our systems, okay? So this 180 psi will oftentimes kind of be where it sits, 160 to 180 for us, and these valves are actually not in play at all. They're not doing anything, right? What is actually keeping the pressure high is the actual sending refrigerant out to the cases. The load isn't demanding enough to keep them out, so it's not like it's flowing in this constant super circle going and going. The TXVs, you see, they are metering or slowing the flow of refrigerant. And remember, right, pressure equals the amount of stuff, can be increased by adding more stuff or increasing the temperature, okay? So if you can't flow to your suction side quick enough, your pressure will increase because now you're adding more stuff. You're bogging down your refrigerant. So what these holdback valves do is during a very low temperature condition, they're just like this. They're an orifice. They're like a little hole, okay, or a certain size hole. And what will happen is as this refrigerant gets to that hole, they won't be able to get through it fast enough. It creates a restriction. So what happens is we're adding more refrigerant on this side of the system, right? And what happens is you're gonna build up liquid refrigerant in this condenser, right? So you might build up like 80% of the condenser is now liquid refrigerant. So what happens is over here in the line, this pressure will kind of go up, right? It will go up to that 155 minimum, whatever these valves are set for. And it will bring that pressure up, and there'll be more gas in these lines over here, which is pushing on that liquid refrigerant. But because only so much refrigerant can escape out of those valves at a time, your pressure will increase, okay? So these create an artificial restriction when it goes below the pressure that these are set to. Now from here we have this, which is the receiver pressure regulator. We saw it in the video. It was the skinny line going out, okay? The receiver pressure regulator regulates, I think you can guess what it does. It regulates the pressure in the receiver, you see, okay? So what happens is if your receiver is sitting for a long time, especially if it's outside, okay? If it's outside, your receiver is going to get very cold, okay? And it's going to lower in pressure because it's going to equalize. Remember, high goes to low. So if you're 0 degrees outside and your receiver is like 40, your receiver's going to be giving off heat to the outside world just because that's how it works. It's just how physics works, okay? So what we do is we feed in discharge gas into this receiver to push the liquid refrigerant out, kind of like a aerosol can, or like when you were a kid and you had those pump squirt guns and you would pump them, it would pump air into the chamber, and then when you press the trigger, it would squirt out all the water. It's the same concept with this with this receiver. So if this receiver goes below a certain value, again, this one isn't really in play. It's only for low temperature conditions, at least in our systems. It's not like it's working all the time. It could be blown. Not saying it couldn't be the issue with your system, but typically these are set to the point where it almost will never be in play just because of the natural flow of the refrigerant. So from there we have a filter dryer. And then we saw that we had a liquid header line coming off, and then we had a liquid header line going to a subcooler and then coming off. So the difference between those two lines is one of them is going to be 70 degrees and one of them is going to be 45 degrees, and we'll go over that in a minute. Now from this liquid header that we saw, we can see that we're going to have a liquid line go out to our case, to our TXV just like we saw, and then to our evaporator, okay? And then from there we're going to go all the way back. We're going to have this EPR valve to our suction header and back to our compressors, okay? And now we're going to go over really quick what is going on in this evap and how does it make cold, okay? We're going to kind of go over that. How is this system making cold? Alrighty, so what happens is, right, because there's some poor guy that sat in a lab for a very long time, he studied liquid and the property of liquid, okay? So if we take water and we boil water, it boils at 212 degrees at atmospheric pressure. Okay, that's like the average, like, if you live in like Texas or something, you boil it in your house, okay, it's going to be like 212. Okay, and it will never increase in temperature. You could put it on, a acetylene torch, you could put it on a stove, you could throw it right on a fire. It will never increase past 212 degrees until it becomes a vapor. Then it will. But now let's say we go up. So the Earth, you can almost view it as like a glorified pipe. You have your atmosphere, and then you have your gas on the inside of your atmosphere. Now, if we're, right on the Earth, like I said, it's going to boil at 212 degrees. Now, if you're on top of Mount Machu Picchu or very tall mountain, because it has less pressure up there, the pressure on the top of the mountain is lower than if you're on a lower plane. It boils at around 200 degrees. Again, you can boil it with whatever you want, as aggressively as you want, and it'll only boil at 200 degrees. So we realize that the boiling temperature is liquid is affected by pressure. So now we have this liquid refrigerant coming to our TXV, and our TXV is allowing the flow of a certain amount of liquid refrigerant. So we know that this liquid refrigerant, right, at 20 psi will boil at negative 20, let's say. Okay? So when this liquid goes into this environment that is 20 psi, right, this liquid refrigerant goes, oh, it's warm enough in order for me to boil. Okay? So it starts boiling or evaporating, but it cannot increase in temperature until it evaporates. Then it can increase in temperature when it's a vapor, but not when it's a liquid. It will stay at negative 20. So that's why when we flow the liquid refrigerant into our evap coil, it stays at negative 20, because physically it cannot increase in temperature until it absorbs enough heat to evaporate. Now, changing a state of matter, so going from a liquid to a gas, is a lot more difficult than increasing the temperature of that matter. So if we had a cup of water and we were going to increase it by 1 degree, okay, that would be 7 times less energy than if we were to evaporate that cup of water. When you evaporate it, you actually have to break bonds between atoms or molecules, and that's a lot harder to do than just increase the temperature. So they found that this was a way that we could create more efficiency out of our system. So what happens is when this liquid is evaporating, right, this EPR is allowing the flow out of the system of these vapor molecules, right, in order to keep it at the pressure needed so that this liquid refrigerant will boil at the temperature that we want it to. So this TXV, what this TXV is doing is it's flowing liquid refrigerant, right? And the engineers somewhere came up and said, okay, wait a minute. We realize that if this increases by 3 degrees, let's say, by the end of this coil, so temperature 1 is negative 20, because that's the boiling point or the evaporation point of this liquid. And then temperature 2 at the end of the coil, let's just use an example of negative 17, right? The engineers, right, will go, okay, at this point, if it increases by 3 degrees, all of the refrigerant will be boiled away by the end of the evaporator coil. And that's all this TXV cares about, is all my liquid refrigerant boiled or evaporated off by the end of the coil, so when it goes back to your compressor, it doesn't slug it. And number 2 is it has a higher efficiency because you're flowing less refrigerant, because these compressors work to flow your refrigerant around the system, okay? And if they have to work harder to flow more refrigerant. So we want to flow as little refrigerant as possible in order to make our system work. So what happens here is this liquid refrigerant, right, outside your case, let's say it's negative 10, and inside your coil it's negative 20. Well, going back to our principle of high goes to low, okay, we're going to have this high temperature, negative 10, naturally go to this low temperature, negative 20. And from there, what happens is your molecules of refrigerant will carry your heat energy, okay? And it will carry your heat energy all the way back to your compressor. And then your compressor will discharge it out, carries that heat energy all the way around, right? And now it has the heat energy from your case, your heat energy from friction, the heat energy from the compressor, the heat energy from your store. Okay, then when it goes to your reclaim tanks, it releases a little bit of that heat energy, which is going to be reused in your hot water. Then from there, it goes to your condenser. Now at that point, it takes that heat energy and it blows it out of the building. Okay, so you're not creating cold, you're moving the warm temperature from inside the building outside the building. Now some of you might think to yourself, well, this doesn't make any sense. How do you go from 45 degrees to negative 20? Okay, when this gas gets put into this evap coil, there's something called flash gas, and I've heard a number thrown out there as 20%. We don't actually know what it could be. It could be anything in there, but I guess 20% is like the sweet spot, supposedly. So what happens is when this liquid refrigerant comes out to this evap coil, it rapidly flashes off and becomes a gas. And in that flashing, it absorbs the heat energy from the other liquid. It absorbs the heat energy from that liquid refrigerant to change state rapidly. So what you're left with is it does flash off, and you're left with a bunch of molecules of vapor that are around 20 degrees, and then you're left with some liquid refrigerant that flows out because there's not enough heat energy here to flash all of it into a vapor. But that's why, especially on low temp, it's so important. That's why we have a subcooler here to lower that line to the right temperature, so we have less of a temperature difference between these two in order to maximize our liquid refrigerant flow. It creates higher efficiency. And that's why for a medium temp rack, at like 55 psi, we could have like a 70 degree, line to the TXV, and it wouldn't affect us that much, as we don't need it to be as cold for the efficiency. Last thing we're going to go over quick is the hot gas, right? So this hot gas differential valves engages, raises the pressure in this line up to 200 psi, and this solenoid activates. The controller says hot gas needed, activates it. Typically hot gas will only be on low temps. Okay, now again, high goes to low. This EPR is no longer engaged, so this is blocked off. So what happens is this high pressure 200 psi flows into this low pressure 20 psi evaporator line, suction line. So this discharge, this hot discharge gas will flow in here, flow all the way around into your evap, and it will use your evap coil, right, because it's in a low temp environment like negative 10, right? It will use your evap coil as a condenser. So now this hot discharge gas will condense down into a liquid, and because it's 200 psi, remember our liquid line's 180 or 155 or whatever it is, and this differential valve raises it around 20 psi higher than the other side of it, which would be, like 180. So because it's a higher pressure, it's able to flow. So it flows, right, around the TXV because there's going to be a bypass, and you have this check valve so the refrigerant doesn't flow backwards. And again, high to low pressure. This is the lower pressure, so it'll flow around your TXV into your liquid and back to your liquid header. It might never actually make it that far, but that's where it's headed, okay? And so that's it. That's the entire rack system kind of summed up, drawn out, and yeah, so that's how you do it. Like and subscribe, and hit that bell.